Right then, I think we're ready to go there. So good morning, everybody. I'm joined here today by Ian Wilcox, the Senior Metrologist from Coventry University, who's going to share his independent expertise in metrology with us and talk to us about why measurement matters so much to the future of manufacturing. And throughout the presentation, you'll hear a series of anecdotes that Ian's going to share with us, and I'm going to contribute to that as well with some stories from PowerINSPECT. And Ian will be sharing with us really 35 years of experience in metrology. He worked for 10 years with Jaguar Cars, and since then he's worked for metrology equipment suppliers for 20 years, and then he spent 5 years in the government skills sector. Now his current position as a senior metrologist for Coventry University's metrology department, he manages the learning and development of their metrology courses and foundation degree. So if we just quickly look at the agenda today, Ian's going to begin by talking to us about the background to Coventry University, who they are and how they've come to have the only UK degree in metrology. I'll talk to you briefly about PowerINSPECT and some of the different machines that we can work with. And then we'll get into the bulk of the presentation, why measurement really matters to the future of manufacturing. And then what are some of the common problems that we see, both from conversations with the Delcam engineers who go out and visit customers and from Ian's experience in metrology. And how can we overcome those problems to achieve a better measurement throughput and to help that contribute to our competitive advantage. So without further ado, I'll hand it over to Ian now, who's going to talk to us briefly about the background to Coventry University.
Good morning, everybody. Yes, as Michael said, my name's Ian Wilcox and I work at the university itself. We're very proud of what we're doing at the university, not only in terms of where we rank within the measures of how good a university is performing here in the UK, but also in terms of our engagement with industry and how we work with our partners and stakeholders around the specific topics within the university. So the university overall, you can read on the screen there, we've done quite well in recent years in terms of these measures and metrics that are put on universities, and one of the big reasons for that is our teaching ability and our student engagement, and also employability rates of students coming out of the university when completed. That's the general university, but then within the university I sit in the metrology team, so there are 9 of us that work in the metrology, and we have a dedicated team that look at supporting engineering, manufacturing in the UK in terms of all metrology, the science of measurement issues, basically from consultancy to research, and a lot of work in learning and development, so short one-day courses right the way up to higher education degrees and foundation degree we do in metrology, which is a unique offer within the UK. So we're very proud of what we do in metrology, and a lot of the companies we work with see us as, in their words, leading lights in this, and we certainly deal with a lot around dimensional metrology, engineering, and so on. Okay.
Okay, so very briefly here, this is largely an educational webinar, but I just want to talk to you very quickly about PowerINSPECT. Now, of course, I'm here on behalf of PowerINSPECT. I work for Delcam. I'm the product marketer, and PowerINSPECT is Delcam's inspection software. It fits in nicely alongside Delcam's suite of advanced manufacturing solutions, in which we've got PowerShape for the CAD package, and then there's PowerMill, of course, which is the world's leading CAM solution. But today, if we look more closely at PowerINSPECT, PowerINSPECT is unique in that it can work with a whole host of different device types. You can see that there are measuring arms in some of the videos, both from companies like Faro and from Roma. We can work with laser scanning solutions, and we can work with laser trackers. You can see an API tracker in one of the videos, but that's not all. We can work with optical devices, with manual CMMs, with CNC CMMs, and with layout machines. Yeah, you can see that in the bottom left-hand corner that there's some probing on a CNC CMM, and then on the left-hand side in the middle, you can see that a Stiefelmeier Ventura machine is used as part of an automotive design process for clay milling and then for inspection of that clay model. So PowerINSPECT's really a versatile inspection solution that can be used in a variety of different measuring environments. So the conversations that I've had with engineers and with our sales staff come from interactions with customers in a whole range of environments and a whole range of applications. So hopefully I'm going to bring some of these anecdotes to the presentation today, and we're going to see what some of the common problems are and how we recommend that people can overcome those problems. So if we begin by looking at why does measurement really matter to the future of manufacturing? So looking back, people would traditionally say that manufacturing is becoming more dispersed. You might have components being manufactured in China, whereas the assembly is in a different factory, or you might have certain different factories within one country, and you want parts to fit correctly first time. Yeah, it can be expensive to have rework or to scrap parts if once they're dispatched from the factory for assembly if they don't fit, and that's particularly key for the UK. Yeah, we're from the EEF data in 2014. It's the 8th largest manufacturer in the world, as you can see on the screen, and manufacturing accounts for 50% of all exports. But measurement is particularly important because we don't only want to control the outputs, that is the parts that are manufactured at the end, but you can also use measurement to monitor the inputs. So this might be to monitor the performance of a machine so that you can tell when factors such as tool wear are deteriorating the performance of the machine. And of course, we want to use measurement to show that parts are fit for purpose. Now, this measurement is particularly important to modern manufacturing because if we look at the developments in some of the manufacturing techniques that are being used, such as additive manufacturing, or there's an increased tendency to use composite parts in manufacturing. And the properties of composite parts they're not the same in all directions and all the axes, and this provides enormous flexibility and difficulty to optimize the design. So really having the measurement processes and being able to capture that data helps us to evidence that the parts are fit for purpose and to control our processes. But through conversations with Ian and with our customers, there are 4 sources of variation that are inherent in any manufacturing process. And what we're going to do today in the presentation is we're going to look at the different sources of variation: equipment, people, environment, and part. And we're going to look at where these sources arise and what we can do to minimize or safeguard against this variation. So the first source of variation that Ian and I are going to look at today is equipment. The NPL have a series of guidance, and they say that you should use the right tools for the job. Now, what does that really mean? It means you should be using equipment and methods that have been demonstrated to be fit for purpose. Ian, what do the NPL really mean by that, fit for purpose and using the right parts, and what examples have you got perhaps that could suggest that a certain piece of equipment might be fit for purpose?
Well, one of the first things we'll look at is the resolution of the equipment. What is it capable of exporting as a result? So, for example, a digital vernier caliper is 2 decimal places of a millimeter. So the resolution of that particular device is 0.01 of a millimeter. So obviously, without even thinking about it, we wouldn't try and measure something that had a tolerance of plus or minus 7 microns with a device that could only measure to resolutions of 10 microns. So the resolution of the equipment is quite important. But then we also have to look at the general capability of the equipment. For example, optical is line of sight. You can only measure what the camera system can actually see. Laser is line of sight. It can only measure what can be achieved. So, for example, barreling inside a hole would not be able to be picked up by a standard optical system or standard laser system. Whereas contact probing, for example, allows you to hook in a little bit below surfaces, so you start to gather maybe some more information. But on CMM, obviously you've got the mechanics of the machine itself. So on a bridge section CMM, as a typical type of CMM, you'll have the roll, yaw and pitch, i.e. the structure of the machine. If you're accelerating quickly and then decelerating quickly, there's a lot of inertia in the machine, and that will cause all sorts of movement inside. So every particular piece of equipment has its own idiosyncrasies, its own variations that we tend to look at.
Okay, yeah. So what you're saying really, Ian, is that each piece of equipment, there are small idiosyncrasies and small problems with each piece of equipment, and that you can't say, for example, I'm inspecting this part and I'm inspecting certain geometry, the part's made of a certain material, therefore I should use this machine. Is that correct, would you say, Ian?
Yeah, very much so. There's certainly some of the contribution. One of the many contributions is hundreds of variables that come into that equation as to what is the best type of equipment. And quite often when we're talking to companies, what we're finding is that they've usually just bought a new piece of equipment and haven't yet learned those idiosyncrasies, or certainly the equipment supplier has not made them aware of those idiosyncrasies. So we'll help them and support them in terms of what they're looking at. And some of the basic tools we give them, for example, on any measuring device that you use, which is a coordinate measuring system. CMM is the term we all use, coordinate measuring machine, but now that's really more than just CMMs. We have optical systems, we have laser trackers, we have articulating arms, CT scanners, photogrammetry, phase light, white light. There's a lot of systems out there now. So we bubble all of those into what we call coordinate metrology systems, but we teach them to look at basically again, 4 main areas at the construct of the machine, the frame. What is the thing that holds this together? What is the mechanical aspects of the machine that it makes up the frame of the system? So in a CMM, that would be the bridge, the granite table, and the column, the Z column, if you like, that comes down from the machine. We then talk to them about the sensor. What is the thing that physically detects the part? So again, on a CMM, that might be a touch trigger probe. You could have a laser stripe scanner. If it's a laser tracker, obviously it's the laser dot, and so on. And then we'll talk about interface, which is software and controller. So is there any sort of manipulation of data? So some of the more modern equipment now is using mass data collection, which means you have filters, averaging going on throughout the system. So there is some form of interface. Even on a dial test indicator, there is an interface, and that interface is you. You're reading the needle on a dial and making an interpretation of whether it's touching the left hand or the right hand indication. So interface is the third, and then the fourth one is the scales, the resolution of the scales. How are the scales performing? And once you understand any coordinate measuring system, once you look at those 4 basics, it's the weak link in the chain, which is the one that's actually going to create you the worst errors. That will usually be the one that would create the overall capability of the system itself. So once you get used to looking at that within any system, you can almost break down any system and start to say, what is its capability? What's it going to be good at? What's it going to be bad at? But then you do need to add things like environmental conditions. Optical systems sometimes don't like light. So if you stick them near a window on a sunny day or it's a cloudy day, you'll get 2 different answers. If it's a contact system, then obviously you've got to worry about the movement of the part, the flexibility of the part, or how you've actually placed the part on the table.
Yeah, that's very interesting, Ian, because some of those topics, such as the environment, of course, we mentioned that as one of the sources of variation, and the part we're going to go on to look at both of those later in the presentation. I just want to jump back really. You mentioned that the stylus selection is particularly key, making sure that you're not using a stylus that's too long, and also you mentioned that there are inherent errors in the CMM, in the scales of the CMM, and one of the example techniques that you've got in many packages of software to minimize the variation in the CMM, in the equipment, is the error mapping that we have in PowerINSPECT. So there are mechanical errors in the CMM, such as the perpendicularity, the parallelism, or the squareness. So, for example, you might have a linear axial variance whereby the y-axis is not exactly perpendicular to the x-axis, and you've got in many packages of software the ability to build a table of compensation values, and the video that you can see here for PowerINSPECT shows how exactly that works. So you've got a known artifact, and you know on that artifact that the machine should, for example, report a value of 10, just to make things very simple. Instead, you can see that your machine might be reporting the value of 9.99875, for example. Now that variance between the 10 and the 9.99875 is the linear axial error. Now what you've got in many software packages that's called error mapping in PowerINSPECT is the ability to take the points on the known artifact, like your calibration sphere, and you can then use those values to build an error map, a table of compensation values, and the machine can then use that table of compensation values throughout the inspection program to increase the repeatability of the inspection program. The error will always be there in the CMM, but by having this table of compensation values, you're able to at least apply that error at a consistent rate so that you know that your inspections are repeatable. And one of the other things that Ian talked about when he was saying that that one of the sources of error is the equipment in itself, he talked about the operator taking the points from the caliper, and that the operator actually taking those points correctly could in itself present an error. Now, one of the things that you've got to look for in a software to ensure that the software is not contributing to that inaccuracy is that the software has been verified. Now, there are two bodies that can be used for software verification. You have the German standard body, which verifies the evaluation of spheres, planes, and cylinders, and you have the American NIST software body, which states whether or not the software is mathematically correct, and that whether the software is giving you the results that it should, whether the algorithms are working correctly. Okay, so moving on to the second source of variation that might arise in an inspection process. We touched upon it there briefly, making sure that the results are recorded correctly, which is typically which is extremely important if you're using older approaches to measurement, but you need to make sure that your measurement staff are competent and qualified and well informed, that procedures are consistent with the international standards in place for all measurements. What exactly does that mean, Ian, to make sure that procedures are in place or that our staff are competent? How's that really important, and why is it such a big issue now?
Well, if we start to look at about the sort of influences that people can have on measurement, we've all heard the old joke of the micrometer being used like a G-clamp over tightening, and how that can change the reading itself. Now obviously the manufacturers try and mitigate this these days by putting either friction drives or ratchet drives onto the micrometers to cut off, if you like, the applied pressure of the user of the gauge. But it's a key thing with all of these sources of variation we're going to talk about. You can never eliminate those variations. You can only mitigate them. You can only dampen their effect, or at least take away the mass of their effect. So, for example, a friction thimble or a ratchet thimble on a micrometer is taking away the mass of the in extra force, if you like, that the operator could apply through that device. But it's still not completely removing it. You know, there is a thing out there at the moment. In fact, MPL will tell you, and we've mentioned MPL a couple of times, we should say National Physical Laboratory, the National Measurement Institute for the UK. So they set the standards. They are the government licensed body that set standards in the UK for, in our case, dimensional measurement. But they'll tell you 1 click on the ratchet is what you should be going for on a micrometer. Anything more than that, and you start to affect your reading. But that effect is quite minimal. I think most companies will go with 3 clicks on a ratchet. But that's one example of that type of procedure, how you can actually set something up so you get consistency. If we go right to the other end of the scale and look at coordinate measure machines, a CNC coordinate measure machine, so an automated machine, we press a button, a program starts, and it measures the components. So you would say at that point, well, what influence is the operator having on that particular measurement? And at that particular constraint, it's none. But of course, that operator has had to load the component on a table, and if they don't quite put it on square, if they don't quite locate it so that there's no shanking, for example, on the probe, then obviously that can have an impact on the set of results. You also need to do qualification. And the qualification process, you know, if the operator is not doing that within a set period of time, then that can start to deteriorate, or things can change, and so on. So these procedures are very important to make sure that you get repetition, that you're actually repeating what you do.
Yeah, so you mentioned that clamping and setting up the part is particularly important. If I'm particularly interested in CNC CMMs, how or what guidance could you give to somebody who is interested in ensuring that their part was set up and clamped in the correct orientation?
Well, first let's set out some parameters here. The first thing I'd want to say before I start this next segment is the human eye is capable of detecting, on average, a typical person, or actually a person with good eyesight, will see 40 microns, no smaller. So you can't see anything physically less than 40 microns in size or movement, for example. So we've all been down the pub and sat down in the pub and stuck our pint on one corner of the table, and the table's rocked over and we've spilled the top inch of our beer. That process is happening with your component. When you put a component down on the table, it's actually sitting on the 3 highest points of that flat face. Let's say you have a flat face. It's being held there by gravity. If you change gravity, i.e. you probe it on a different part, you put a force onto that component on a different area, it may be balanced in such a way that it then rocks over onto another point to create a new 3-point section. If that's less than 40 microns, you don't see it, so you can't actually see the component move. But 40 microns is enough to make a difference to a lot of people's tolerances these days. So that's one thing, is, you know, why do we clamp components? We clamp them so they don't move. If we're applying or exerting any force, obviously if you're using optics, lasers, you're not applying force, but if you're using contact systems, you're applying force. So we clamp it to make sure that the component isn't moving, even within this 40 microns that we've just talked about. And so it becomes very important to look at that clamping strategy. Some companies I know will go to the full extreme of placing a torque tolerance onto their clamping, so that they're not actually over-stressing or distorting the component by any clamping forces that they're using.
Okay, yeah, very interesting. So we've kind of jumped ahead a little bit there, and we moved on to the third of those 3 bullet points to say that the error might come from clamping or part setup in the variation. I'm going to talk a little bit about how probing strategy and the number and position of the measured points can also influence the results. For example, if you're not taking enough points for a plane to get a good representation of that plane. I'm going to show how software can contribute to minimize that variance. So in many inspection softwares now, there are, of course, embedded strategies that tell you have to, for example, take a minimum of 3 points for a plane, or you might have to, for a perhaps more complex geometric shape, like a cone, for example, you've got to take a minimum of 6 points so that the algorithms can calculate a true representation of that. We also talked about using the right people and the right using the right people and making sure that they're competent and well informed about the processes that they have to use. So one of the example techniques, of course, there is to send them on a course. Yep, there are online resources available to help people with their inspections, but these are few and far between. There are now, of course, in places like the UK, there are courses from the NPL, National Physics Laboratory, as well as from places like Coventry University. And these are some of the examples of ways that you can ensure that the people are well informed and qualified to conduct your measurement processes. So we now move on and look at measurement consistency and how the software can contribute to ensure that we're taking enough points, or that we're taking points in the correct places. So there are things in many software packages, particularly when we're using portable measurement equipment, we need to make sure, because it's not an automated process and it requires the user to physically bring the probe into contact with the point or to laser scan the correct location on the part, then we need to use the software to some extent to make sure that that process is repeatable, that the points are being taken in the same places every time. Now, one of the ways that this works in the software is that there are things like guided measurements, whereby you can use audible and visual aids to direct the user to a certain point. For example, you can see in the video there that the part's been laser scanned, and then we want to take some points with a tactile probe. Now in PowerINSPECT, you could laser scan the part, and then one of the new pieces of functionality that we've got in PowerINSPECT 2015 R2 is this guiding line. You might be able to see a blue line between the arrow and where the actual probe point is, and as you bring the probe closer to where you're supposed to take that point, that blue line moves. Yeah, and that's complemented by an audible aid, so you hear as well as see when you're getting close to where the point should be taken. And one of the benefits of this is to make sure that the points are taken in the same place for each component that you're inspecting, and therefore, of course, it's a more repeatable inspection process.
Just a little point on there. One of the most common calls we get from engineering companies is when there's a dispute between themselves and their customer or their supplier in terms of, look, I've got a X machine and I'm measuring it on that, and you've got a Y machine and you're measuring it on that, and yet we get different numbers, and they'll get into a bit of a spiral of who's right and who's wrong. And what we actually find when we're called into those situations is actually they're both right, but they're both measuring it a different way. So your strategy in terms of how many points you take and where you take your points will make a big difference. And this ties in 2 or 3 things we've already talked about. One is setting good procedures, making sure that you have an understanding of what you're trying to achieve and how you're going to achieve it. But the second one is basically this part and the part influence on the variation itself, which I know we're going to talk about in a minute anyway. But so it's very important to look at this probing strategy. And if you only take 6 or 7 points on a plane, you're not seeing all of the flatness of that plane. You're only seeing the flatness over those 6 or 7 points. If you've got a laser stripe scanner that's taking thousands of points per second, then obviously you're capturing much more data about the surface, although we would also talk about the variation on those individual points that you might be seeing, and the filtering and so on that has to go on behind that. But ultimately that That is one of the most common things we get called into, is this, that, I've measured it with 7 points. Oh, well, I've measured it in 6. Well, I took my 7 here, or I took my 6 here, and we got different answers. Well, no surprise. That strategy of where you take your points and how you take your points can make a big difference to the result because of part variation.
Okay, that's interesting stuff. So we've seen that the points where you actually take them, and the number of points that you take are key to achieving repeatable measurements. And really, a lot of what we're talking about here is achieving repeatability as much as anything. We're looking at minimizing the sources of variation, factors that change, external factors which change, so that we can ensure that we're getting the same results every time for every part that we measure. And for PowerINSPECT, a lot of the work that we've done has been on the shop floor, and these are often in locations where the temperature can change quite easily, and that's a huge problem for somebody inspecting a part, because particularly if you're using some of the more modern manufacturing techniques, of course, at hotter temperatures that part can be larger, and at colder temperatures it might be slightly smaller. So the NPL say that measurements made in one location need to be consistent with those made elsewhere. That is not necessarily to say that we need to inspect in an ambient environment, because again that causes problems for us. Yeah, when we first saw the problems of temperature variation, one of the answers was to inspect your components in ambient conditions. But what problems does that bring to an organization here? And if they have to inspect those in ambient conditions, of course it minimizes the variation, but what are the problems that it can bring as well?
Well, I mean, there's a whole variety of issues around that, and we tend to talk about environment, but I'll give 4 particular examples. We'll start off with light. If you're using an optical system, photogrammetry, anything that uses or captures a picture of the particular part, then variation in light can actually change how the system is therefore seeing the component. So lighting can be one of 4 major factors we constantly see. Dirt and dust, swarf, oil, obviously debris, particulates, whatever you want to call it, on the component itself, but also on the measuring equipment, obviously, so the cleanliness of component can be an issue. We'll also talk about vibration. If we have a dial test indicator, a 1 micron dial test indicator on a gauge block pile, and a lorry drives past in the roadway next to your building, you can actually see the needle quiver on the dial test indicator, and that's the vibration coming up through the floor and being fed right the way through to your sensor, your measuring device, in this case, dial test indicator. What happens quite often with digital equipment is that same vibration is happening, but you don't see it because that digital equipment is pulsing a result. It's almost like taking a picture of your dial test indicator as it vibrates. You only see at that particular microsecond what the needle was pointing at. And so you can get error from vibration, and that's quite often masked by digital systems. So also look at big tumble deburrers, presses, anything that's in the locale of measuring devices can have an effect on vibration. But the temperature is the one that we talked about initially there. Metal components, mostly metal components, but pretty much everything generally, but it's seen most effectively in metal, is if it gets warm, it expands. If it gets cold, it contracts. So you get this variation. And people often talk about, yes, but if it's 25 degrees in the factory, I can sort of work out a rough compensation for that expansion of material. But very often in a general shop floor environment, that temperature is not static, it's constantly moving. So it doesn't start at 20, jump to 25, stay there for 2 hours, then jump back down to 21 and stay there for 2 hours. There is a constant wave of change in temperature. And every component has different properties, how many holes are in it, what the wall thicknesses are. And of course, all components have varying wall thicknesses. There'll be solid lumps in the middle of the component, but then there'll be areas where there's very thin walls. They all move at different rates. They're all changing more rapidly and slowing down. And so the part is constantly trying to keep up with the variation of temperature, but it's keeping up with it at different speeds. And so that can make a challenge for measurement generally. If you can say that your shop floor has a reasonably steady flow of change in temperature, i.e. at 9 o'clock in the morning it's 18 degrees, by 3 in the afternoon it's 26 degrees, and we've had a steady sort of almost sinusoidal wave of change over that 24-hour period, then you can start to look at compensating for it.
Well, of course, we all know that some of the portable CMM manufacturers have released devices that have got a temperature compensation sensor in them, and PowerINSPECT, like many softwares, has the ability to factor in that temperature compensation to measurements. We mentioned that ambient rooms might be one option if we were inspecting on the shop floor, but the downside to that is that the part have to soak, which is a huge problem for throughput, because typically, what would you say, in that parts perhaps have to soak for 24 hours or so to normalize to the conditions in the ambient room?
If you take a calibration lab, then yes, they'll soak a component overnight or 24 hours, depending on the size of the component, to be absolutely certain it's changed to the ambient temperature of that particular room. But you do have to be careful saying any fixed hours, because a kilogram of plastic will change at a slower rate than a kilogram of aluminium, for example. So we need to look at a bit about the materials, a bit about the environment itself. Is there constant movement of air, in which case it'll change temperature quickly. If you put the component, particularly metal components, onto a metal plate or a metal shelf, it will change temperature quicker.
Yeah, absolutely. But all the same, whether that's a metal component or a plastic component, one of the problems is that we have to soak that component for a certain amount of time, which damages the throughput. And obviously it's a bottleneck then in our manufacturing process, which isn't great for our efficiency. So we mentioned that a lot of software and hardware compensate for temperature variations. In the video here in PowerINSPECT, what happens is you can create a new measure and say that I'm measuring this part at, for example, 1 degrees. You might then know that the part is going to be used at a temperature of 65 degrees. For example, an aerospace blade, you might know that the temperature that you're measuring at is going to be significantly lower than when that blade is actually in the aeroplane. So you can then report on what the value would be at the future temperature. So this helps us to offset some of the uncertainty which surrounds temperature variations.
Well, I mean, in the standards, everything technically should be measured to 20 degrees. So you should be trying to measure a component as if it was sitting at 20 degrees C, centigrade. And if you can't measure it at that, then you have to look at compensation through software or manual compensation. There is a formula, but if you've got the software to do that formula for you, obviously that's a lot better. But you're trying to get a number that would be the component at 20 degrees. And that's actually, if you're working to the international standards ISO, that's ISO 1. ISO 1 sets the temperature at 20 degrees that measurement should take place, and that gives us a consistency around the world, whether you're in Finland, South Africa or the Sahara Desert. If you're measuring a component, you should be looking to give a result as the component would be at 20 degrees C. Okay.
So the final area of variation that we talked about at the start was variation in the part itself. Of course, the different techniques that we're using to manufacture that part can influence the variation. For example, castings are typically less accurate than machine parts, and composite parts, as we mentioned, they are anisotropic in their very nature, so that makes the inherent variation in their surface properties more difficult.
Sorry, just one quick point on that. You cannot underestimate how much the component itself will have a variation on your measurement. So, for example, if you're measuring the thickness of a simple block that's 100 millimeters long, there won't be parallel faces. Those faces that you're measuring across won't be parallel. If you measure at one end of the component, you get a different number than if you measure at the other end of the component. So that's where the part can add variance. Unless you have a procedure that says, look, we're always going to measure at the right-hand end or in the middle, or take the two readings and average, or even show the range, you will always get variation. And this casting is a great example. If I give people a micrometer with a 1 micron resolution and ask them to measure a gauge block, a slip, a 10 mil slip, they'll get repeatability to 2 or 3 microns. So resolution of the equipment, 1 micron, 2 or 3 microns over a group of people. But if I gave them a cast slip of 10 millimeters, by cast I mean you can see the pot marks, you can see the pitting on the surface, it's just a cast surface, then I can see 20, 30 microns variance across those people, because that pitting will have an effect, the surface texture, if you like, will have an effect on the ability of the equipment to give you a constant figure. So you will always see variation through the part, and it's certainly in a lot of cases a large influence of variation in measurement processes, particularly manual measurement processes.
Okay, thank you, Ian. Some very good insights there. And that brings us to the end of the webinar. We hope you've enjoyed today's session. The webinar will be distributed to all of those people who registered in the next few days. We'll be sending a thank you mailer, and there will be a download link where you can watch the webinar again. Please do stay in touch with us. This is one of a series of webinars that PowerINSPECT are hosting throughout the year, and you can see more information on our powerinspect.com/webinars website address. We're hoping to discuss various industry topics and bring in some key speakers like Ian to hear their views on some of the developments in inspection techniques and in the new releases of hardware and software. If you would like to find more about metrology courses, Coventry University hosts a whole range of different courses that I'm sure Ian could tell us a lot more about.
Yes, I mean, obviously as I said earlier on, we do a whole set of courses from one day in terms of introductions to various topics underpinning metrology, right the way up to our foundation degree in metrology, which is a higher education award, undergraduate award for metrology itself. And I say we do, well, as we said on the first slide there, it's over 1,000 people a year. We train students as well as companies and themselves.
And people can find out more information about that on the Coventry University website, of course.
Yes. If you drop onto our website or contact me through the website or even through LinkedIn, any other way you can get hold of me, then I'll happily talk to you about that. And we also build a lot of bespoke courses, so we actually train 5 of the OEMs that manufacture equipment actually come to us, and their staff are trained, their application and their sales staff actually get training on metrology from us, as well as Rolls-Royce, Jaguar Land Rover. There's a whole host of companies from the very large to the very small SMEs, sometimes 1 or 2 man bands that we look after both through consultancy and training and a bit of research.
Okay, and then the final resource that we've referred to today is, of course, the NPL, and you can find more information on metrology on their website, npl.co.uk.